So when this was billed as an open session, I foolishly thought we were going to spend time discussing open questions. I mean, so there's 3. Maybe people could suggest some more.
Yeah.
I'd be very interested.
Okay. Yeah.
So, I wasn't sure what the format of this would be, but
No, I mean now.
But let me, so with the possibility of writing, obviously, one thing I want to talk about 2 things which already came up. So one is the point I keep repeating to any audience like this, I mean many of you are anyway doing it, is that maybe it looks more and more like determinant is hard and we should understand simpler objects and simpler polynomials. And if you think from the point of view of computational complexity theory, we cannot even prove lower bounds for things that look like this. And we have products of linear forms. Well, these are fine. As far as we know, it's possible that determinant M or even permanent M is much more outrageous than determinant of permanent itself. It's possible that you can embed them with, with just n things here where n is poly m. As far as we know, you can compute determinant and permanent just by a formula of polynomial size of depth 3, which looks like this and just has affine forms in the variable. It's outrageous, and we should prove that that's impossible. So we don't know how to. So let me give you an easier problem. An easier problem follows from the fact that the elementary symmetric polynomials in n variables. So I basically want you to study this guy as opposed to the determinant. The orbit closure of this guy.
What is it exactly? You want to study orbit closure of under what?
Under
GLA?
affine, well, AN. Under affine subgroup because I have to allow. So it turns out that these are polynomials which look complicated. They have exponentially many monomials, but nevertheless there is a very simple formula like this. The very simple formula just with n and n. So despite the fact that this is complicated polynomial, I can show you this very beautiful result of the norm. Anyway, it's a fact. So, what? I can show you. But let me just a second, but because of that, an even easier question to ask is, you are answering him, Joseph, are you answering?
Yeah, I was telling you.
I can answer everybody.
Okay, so it's one of those.
But I can just let me finish the sentence, then I can show you. Because this can be done. An even easier question to ask is, can you embed determinant or permanent or your favorite polynomial not into this, but just into the symmetric polynomial of linear form? So can you write that m as the elementary symmetric polynomial for some k and n polynomial in m of some linear forms in this variable? So this is an m by m matrix which has variables, I don't know, y, j. So this will be
And what kind of
the y.
What kind of lower bounds for n and k would make you happy?
Super polynomial. Super polynomial.
So you cannot do it for n and k polynomials in M. That would be the...
Yeah, well, k is less than n, so you cannot do it for n, which is polynomial.
So these are affine?
Affine forms. It's very important that they are affine Joseph talks about the method of partial derivatives, which is the baby version of everything that Eyal was doing, is something that Noam, Nissan, and I did long ago. You can use it to show that if you restrict yourself to homogeneous linear form without constants, then there is an exponential lower bound on embedding even the determinant into this term. There's an exponential lower bound. But once you allow constants, and now I'll answer your question because you see the power of constants. You can get polynomial size formulas for this elementary symmetric polynomials. Not for determinant, maybe, I don't know, but definitely for. So, just want to say that this is just a question of whether the determinant is contained in the determinant M is contained in the action of the affine group on acting on the symmetric polynomial without talking generality with symmetric polynomial. So we just, we want to understand whether you can. It's the same kind of question we keep asking. I mean, the whole week we were asking about determinant. It's a much simpler polynomial, the elementary symmetric polynomial.
I think maybe the orbit closure of that doesn't contain any nasty stuff.
Yeah. So it's a great question whether your conjecture about the orbit closure
won't hold for it. I mean,
So you expect, so here's a great conjecture, which in fact I was going to suggest. Show that this closure does not have any wild stuff. So elementary symmetric polynomials. All the things in the closure of small circuits. I think it makes sense. I didn't try. I don't think it will be easy, but I think it's much more doable than for the determinant. So I'm suggesting this.
May I ask the notation? Does n mean?
Yeah, n is polynomial in. So you want to show this?
And what is n? What kind of group?
Oh no, this is just a fine group. So you.
Translation.
Translation.
Yeah.
I see.
So you just. Well, this is the way I like to express it. Just write it as a symmetric function of affine forms.
An elementary symmetric function.
Elementary symmetric function. One of the elementary symmetric functions. With no loss of generality takes the minimum.
I think the other similar thing is that for diagonal Dave-tree circuits, which geometers know about, it does not contain points with slope in the circuit size.
Yeah, I should have mentioned that even simpler objects than elementary symmetric polynomials are just a diagonal sum of powers.
Yeah.
And for that we have lower.
No, but on the boundary.
On the boundary, I don't know. Actually, yeah, that's it. Yeah. So, yeah, it starts from the most.
We know that there are no bad points?
He's the one. He should be.
So may we rephrase your question about characters of GL? So they seem sure polynomials when the Young diagram has only rows and the determinant has only one column. No, it's this. Okay.
Yeah. For me, it's less natural, but maybe for you, it's more natural to think about it this way. Anyway, yeah. So there are simple polynomials to study and to study the closure and so on. Now, for those who want to see this is sort of real magic, but it's very simple. So here's the circuit. It comes from the fact that you all know that if I take some values, I have my variables x1 to xn, I want one of the elementary symmetric polynomials in it, I'll compute them all in fact. So I take some variable t, and I look at this product, t plus x1,
Generic function.
t plus xn, this is just simply the sum of the symmetric. Okay, and here we have whatever t to the n minus, right? So this is in the xi. That's obvious, but that's great. This is the circuit. You see the circuit. So the multiplication gate. I'll tell you what the addition gate. So we'll have n plus 1 multiplication gate. All will look like this. So here it will do, let's say, we take, this will be responsible for t equals 0. I'm going to do interpolation. So here I go simply x1.
Oh, I see that,
x1.
that's how you're gonna recover the.
xn. Here I multiply 1 plus x1, 1 plus xn, and here I multiply n plus. I need the field to be larger than n. So I just evaluate this for different values of t. Now what do I put here? Well, if I have all these values, I have evaluations of this at n plus 1 points. For any fixed k, I can tell you what, there is some constant here.
Okay, that's
it.
fine.
Right?
Okay.
So it's an n squared size formula for the symmetry.
But I don't understand, you ask us to express the determinant as a symmetric polynomial in linear forms, and you just said above that that's hard.
Yeah, no, so what I'm saying, this is a way to do the symmetric, elementary symmetric ones. And I wanted to show that nothing like this could work.
Oh, I see, this
determinant
should be
or
an
permanent.
impossibility.
Yeah.
I understand.
Yeah, we
That's
don't-
the point. Yeah, it's too simple.
Now, you can notice that, the linear forms here have just two, are of size 2. So you can start, like we always start with easier problems and try to say, well, maybe if there are 2 or 3 or constant, it cannot be done. And Niraj has a new result showing that if this is small, let's say constant, this requires exponential size. But this exponential lower bound breaks down when the final grows. I don't know to say it exactly. Anyway, that was one thing I wanted to ask. Just study these simpler reductions to simpler polynomials. The other thing I mentioned during Joseph's talk, so I'm not going to write anything down, I'll just say it again. All the lower bound methods which succeeded for some classes of circuits have a common framework. The common framework is that we take, just write one line. All the ones that were successful, and also many of the ones that Joseph described that are being attempted by various people, all these young flattenings and all these other things. They have the same form. They take, if we take, I don't know, p with n variables and degree d. So these are all polynomials. All polynomials in n variables, homogeneous of degree d. I know you like SG of, but it doesn't matter. Anyway, we have this space, and we take a linear mapping from this to some vectors, whatever we want. So this is a linear mapping. And the way we prove lower bounds is we let's say for polynomial p, we want to say that the dimension of L of p is bigger than the dimension of anything trying to compute it. It can be a family of circuits, it can be the closure of determinant under, it's just a set of, so it's bigger than the dimension of L of Q, of course, Q in some class Q, which is what we are trying to, prove the lower bound. That's how they work. I think it's a great question. So partial derivatives like this, and shifted ones are like the shifted partial derivatives, and the projected shifted partial derivatives are like that, and the young flattenings are like that. And it's
So this is upper semi-continuity that the dimension of the image can only drop.
no, not necessarily. Not necessarily, but that's how the proofs work.
Generation.
This is
Under
bigger.
generation, the dimension of the image can only drop.
Right. But anyway, you are trying to do something like this, and one question I don't know the answer to. I think it's a great question. I think the feeling I have, and maybe Joseph shares the same feeling, is that linear maps may not be enough. So it's it would be a great question to say that no matter what linear, you just study it in complete generality. No matter what linear maps you cannot use it to separate permanent from determinant.
But if you have a nonlinear map with that dimension, you call it, you look at the tangent spaces.
Exactly.
I mean,
So excuse me, if you have a nonlinear map of that property, then you look at the tangent space,
You got a linear map.
you then get a linear map.
yes.
So why would nonlinear be better then?
Or even non-linear map can be completely changed into linear map by going to symmetric power.
Yeah.
Well, but I think what,
Well,
I
but
think
it-
what's hidden in what Avi didn't say is that there's this determinantal property that.
Yeah, that's why that has to be
It's-
made
it's that it's-
precise.
Yeah, you're right, because,
Amounts to computing a
otherwise you can
determinant
do
with
this
linear
thing.
entries.
Yeah, you need to, limit the families. The families you allow, but, I mean, let's say the family choose, all polynomial size formulas or just, translations of determinant of small size, of polynomial size. Then, yeah, so you can study it specifically, Here is a specific question. I didn't think about, so maybe I'm not stating it right, but something like that. Does there exist an L for which the dimension of L of the permanent, or you need actually the padded permanent? The padded permanent is bigger than the dimension of anything, any cube in whatever. How does it, that's how you know. And so in the Orbis closure of the determinant from n variables or n polynomial. Is there any map which will distinguish? I don't know. I mean, that's a concrete question. And this here, I think that it's not the same question to move to, if I replace it by some polynomial map. It's not, anyway, I don't know what it would even mean. It's a polynomial map, and it will not be a vector space, but you're going from. Anyway.
So it's probably true that you can always distinguish with some linear maps. Because if you have any object, you can always construct some linear maps.
Yes, that is the thing.
But not,
Let me
maybe not just by the dimension.
Yeah,
That's not-
I should say, I didn't like, I mean, what this map, we have some fixed vector space, and what we are mapping is to subspaces outside, We are mapping polynomials to subspaces of this vector. That's what happens in all this.
I understand it, because it's a family of maps.
Yeah, exactly. So, yeah, and that's a concrete question. Maybe it's not precisely formulated, but I would love to know whether.
But the way that works is that's sort of a continuous map of polynomials.
Yeah.
There's an oversum continuity dimension.
So do you have some
And that's what you're
specific
taking
L in
advantage of.
mind
But
which
can't you
might be
rewrite
good?
something like
No, I wonder whether there is any.
Can't look at this- look at all
I
the
don't know.
tangent
Maybe
spaces.
there is no evidence. Maybe there is. I mean, I don't know, but I find it very interesting.
No.
What's the limit? I mean, we have
There'd be points which are
complexity
very
some.
Which is essentially good for both maps, I guess.
We are very, how do you say, reflective or science in that when we fail to prove something, we try to look for the reason, namely prove that all the methods we use so far fail. There is a history of such things, and some of you have heard of natural proofs and relativization and various things like this. So this would be, maybe this is not this technique in general, no matter what kind of, algebraic geometric intuition you have, it will, linear is not enough. I don't know. I think I took more time than any of you wanted to take, so.
Thank you very much. So, any comments or questions?
Well, I was going to mention a question of K-tons, because
Yeah.
I think I can say it for algebraic geometers. So it's too bad, because Frank Bleckerman will be here, but he's not here at the moment. This is really a question for him. So there's this variety of Veronese. which is just the d powers. And then you have this symmetric order rank, which is the smallest r, or the wearing rank of P, the smallest, so P polynomial. It's the smallest r such that P is some x1 to the d plus to the d. So this is, let's call that r, and then we have r under bar, the smallest r such that P is a limit of things like this. So these are things of rank, at most, rank r. These are things of rank, order rank r. And the question is how different can these two numbers be? So does there exist a sequence J where the growth of Pj is greater than a polynomial in the growth of the order rank? And the conjecture is no.
These two ranks should coincide.
No, they do not coincide in general.
Then what do you think?
So the order rank can, so if I look at the polynomial x squared, x to the d minus 1y, that has order rank equal to 2, and rank equal to, what is it, d minus 1 or d over 2, something like that.
D is D.
What?
D.
D. I knew it was something like that. So here you have 2 and d, so they could be very different, but still d grows like a polynomial.
A polynomial in 2?
All right, so I have to make the question more precise.
Yeah, so because the second
I think it is a polynomial in d in the number of variables.
Yeah, so polynomial
in d in number of variables. Or whatever.
No, but it has to be made precise, though.
Yeah, no, I agree. It should be made precise.
Yeah.
So, yeah, so let's,
Otherwise, the answer is true.
Exactly.
yeah, so let's see. So we have n, the number of variables, and d, but you could let's just set n equal to d without any loss of generality, so we only have one parameter to worry about. And so what we want is a big gap between these two that grows faster than the polynomial. So r of pj minus r of pj greater than poly.
The word difference doesn't sound
The fixed D, yes?
Ratio, that's what I meant. Yeah, I'm getting there.
What's the,
Another month and I'll have it said precisely.
what's the, I mean, how fast do these rings grow in general?
It's completely unknown. The only thing
No,
that is
not the quotient, I mean the bigger one, but
The bigger
what's
one-
the maximum rank?
the maximum rank is known to be at most twice the maximum border rank. So,
Yes.
but of course the maximum border rank can grow exponentially fast in n. So you want to, so if there's going to be a counterexample, it's going to be something of smallish order rank where the rank is close to maximal. That's the idea.
So what's the maximum rank? Where's that?
I told you, the only thing that's known is it's at most twice the maximal border rank, and the maximal border rank is this, n plus d minus 1 choose d divided by what? N.
But you want the minimum border rank and the maximum
I
rank.
understand what this is.
You want the minimum border rank and the maximum rank.
Yeah.
Right. The ratio to be maximized. And that grow very fast.
Okay.
That's Keitan's question. He believes no. I think that's reasonable. And I think this is a very clean question in algebraic geometry that we could work on.
So I have a question about this Kp and P. I mean, that's motivated in part by your result on Littlewood-Richardson coefficients, but is there any other reason besides its hope for that?
That NNL is in P.
The Kp, no, Kp is in P.
Yeah, but the intuition comes from
The previous one.
yeah. My intuition. I mean, not the Littlewood-Richardson coefficient. There is a big gap between Littlewood-Richardson.
Yes.
On that result. NNL for delta Z10 is in P if whatever the complexity theory conjecture. Okay. And this is actually in some sense easier form of that because here you have to battle with all the horror on the border and all that. Yeah.
Okay.
And if this is not easy, then I think that this won't be easy, and if that is not easy in this way.
I couldn't hear it. That's the conversation.
You couldn't hear? Okay. What I'm saying is that if this is not in P, it's very unlikely that this is in P.
Okay.
All the things that I talked about, which none of us want to happen, would happen, and I think that none of those things would happen.
Like in this talk, like it's covered like a very big field in complexity, which is the polynomial and edge testing with randomization. And it's like in fact there is a theorem which not formally but which shows if you know how to make polynomial density testing or how to make the randomization, you can separate permanent from determinant. It's not completely formal, and I want like to note one very nice problem in the randomization. So the problem is the following. Assume that you have a polynomial p of x in p of x1, x2, so on, till xn, and I want to find one concrete polynomial which is not zero, not identically zero on any subspace of dimension, say 10. What's the minimal degree of this polynomial can you find? So
You have a polynomial which is
I want to find polynomial in n variables. So such that for every vector space,
That's the final variety.
of dimension say 10, p of x1 to xn restricted to v is not identically zero. This, in my opinion, it's a very clean question. Like dimension, so making dimension argument, one can show that there exists such polynomial. One can show that exists such polynomial of degree n to the 1 over 10.
What is unique?
He doesn't mean he just says it exists.
Exists.
So once you get up there, a generic polynomial will have that property.
Yes, generic polynomial will have this property. Now, like very
what did you write degree?
yes, degree.
This one with the degrees that side.
Yes. Degree of inside. You can say exactly what's going on.
Order of, no, I can't read. Order n to the power 1 by 10?
Yes.
Yes. So I'm saying that dimension argument say that generic polynomial has this property that
But what happened with the symmetric, elementary symmetric polynomial of degree 11?
it will be zero. I can show
For
that
what?
on some subspace. Yes. Like it's maybe not trivial to find subspace, but like you can show if degree is too small, like if degree is less than
No,
n.
just above your dimension, one above your dimension.
No, he says n to the 1/10. No?
I know, but I'm giving an even lower,
Much
cheaper.
better.
Well,
yeah.
if it's slower, you can show that there is not. I can show proof. And the reason it's actually dimension argument because like if you work over complex numbers, you can show that there is not exist such polynomial. And so this polynomial degree approximately
Harris.
10 to 1/10 this property. And like reason why we need such degrees, because if you look say on P of lambda 1 V plus lambda 2 V lambda 10 V, you expand it as polynomial in lambdas, you get here some polynomial with I1 plus I2 plus I10 equal to D of lambda to the power I. Here will be some polynomials P, Pi. You'll expand it this way. And it's zero if and only if all these polynomials are zero at some point. Like it's V1. V10, but it's zero if all these polynomials you can find like some points in V1, V2, V10, such that all these polynomials will be zero. So you cannot take it's too small. But we can find such polynomial, like we can show it for generic polynomial with degree will have this property. And it looks very clean question, and it will have like many implications, like in generalization of polynomial density, for error correcting codes, like, and it's like there are many other questions which just.
So for if dimension was not 10 but 1, you would take the moment.
Yes, then dimension 1 you can solve it, and for dimension 2 you can also solve it, not more. Maybe I have other questions from the organization.
So I mean this should, if it happens, if there's some degree where it happens, then it should happen for general polynomial. Because you could use
it's happened for it's true for generic polynomial. The question is to find like explicitly to find one and to prove for this one that it's not zero.
Okay, I see. I see. Not to find the lowest degree where this can occur. But
No, it's very again in a haste.
Yeah. Okay. Sure.
I really like it.
So what, Carlo?
That's a great one.
That's a great one.
What?
So what does it mean?
What's mean explicit? So it's a question that was discussed many times, and in any sense that it's look. So let's say find any polynomial, but don't say generic polynomial. Generic polynomial is not explicit. Dimension argument is not allowed. Dimension or random arguments are not allowed.
So, but the number of coefficients is exponential.
Yes, but it's okay. It's okay. So show like there is many ways to like so there is an algorithm which writes coefficient of each monomial in polynomial time. But
I think in many people use, I think in shallow depth circuit, they think explicit if it is in sharp fit. Is that what it is?
It's
Like
in
permanent
P to write. It's in P to write down the coefficient. Every coefficient.
Yes, that is uniform BNP.
Yeah, uniform BNP.
Uniform BNP. That is what.
Yeah.
Correct. Exactly.
So the coefficients can be exponentially large or something?
No. Coefficient you can write down efficiently.
you have to write down coefficient efficiently. So I will not allow you to make tricks like taking coefficients like irrational numbers or So no cheating like this, like or taking coefficients which are E or.
Why don't you just say uniform BNP? Uniform BNP. I think they would.
Yeah, like permanent.
Yes.
Permanent
Yes,
has exponentially many monomials, but it's not a problem to know what it is.
Have you tried asking Nathan? Because he gave a talk about Nathan, who gave a talk about Fano schemes in hypersurfaces. And this is a question when
Okay, this why I'm asking this question now because I don't know.
Nathan left today morning.
His co-authors were in front of you, I believe.
Yes, sorry. Because this is a question, yes, for finding
When is the
hypersurface
Fano
with
scheme?
empty Fano scheme.
But write one down that has an empty
Explicit thing with empty Fano scheme is,
probably want
But
more, yeah,
if-
small
Still, I would-
coefficient.
But
I would
following
ask-
your idea, if there's some, there could be some interesting, linear section or manipulation one could do to the permanent to kill its Fano scheme, that would be a way to take their paper as a starting point. You look at where those Fano schemes come from because they know where they come from, in some cases for the permanent. And then you try to kill those off one by altering the permanent. That would be one strategy.
So I don't know precise results, but in the morning, Nathan told me that like Fano schemes of hypersurfaces are studied.
Oh, yeah, well,
Yes.
Well known that you can
Those people that,
make integers which are large exponential large behave by some high argument like generic complex numbers, right? So
Yeah.
but you don't allow this kind of.
No.
yeah, that's the sort of problem.
You need some.
So what is the model? I mean, coefficients.
should be some small.
Can you compute it in polynomial time?
Yes, so you can,
Polynomial
so
model.
every, so let's say, for every monomial,
Probably the height.
every monomial,
Having this conversation all week long.
alpha, like,
Factory,
efficient.
No, the other order of quantifier, there is an efficient algorithm
Yeah.
which is when given the description of alpha.
Yeah, because for every
I realize.
Exist efficient algorithm such that it's alpha and gives Ci.
But efficient in what model?
Efficient to say polynomial. So look, find say-
Polynomial in the index of the
You
location.
just notice that the description of alpha is just a sequence of integers, right? So the input is just a sequence of integers, the exponent. And what, so this algorithm, the normal model, your favorite computer program.
Yes, for instance.
Any computer program that takes integers and produces, let's say it's a 0-1 polynomial, insist on a 0. We'll just say 0.
But the Fermat surface, the Fermat surface,
Yeah, it can add, multiply as long as it's polynomial time.
plus x m to the some m.
No. You count.
X to the m.
No, it's
plus
not
x to the m. Fermat surface.
It's a bit model. You count down. Yeah.
I don't think it's for master, I think I checked it, and for which specific polynomial it doesn't work, but I don't remember what's exact surface or at 0.
Yeah, you can, then I would just say a few words as a chair.
Okay, so well, it's time to end this conference, I think, so we had a very intense week, and I would like to thank all the participants for sharing.
And as the chair of the GCT workshop committee, on behalf of the committee, I would like to thank all the speakers for the great talks, for all the participants for their enthusiasm, for making this workshop a success. Thank you.
And maybe we should thank the organizers for the great job.